Okay, so what we've...
do you want the lights on?
I think it's okay. Is that okay? It's a bit. I've got it a bit larger than yesterday, and the screen's a bit better. But so what we saw in the lab session earlier, we did this sort of sampling in this two-stage process where we took some parameters, sampled W from the prior over parameters, and then we said, well, F is equal to these basis matrix, and n by m, where m is the number of basis functions times W. And then we just computed that and plotted the result. But what we've just been saying in the lectures is, well, if we believe in multivariate Gaussians, which we do, then we know directly that F is drawn from this Gaussian density with this direct marginal likelihood. So we should be able to sample directly from that density. Right? So rather than sampling W, if everything we say is true, and some of the exercises early in the lab are about showing that that's true for simple cases, you can go back and look at those. And so what we're doing down here, and I guess the worry is that I'll press return and I won't have the right stuff loaded in, but let's see. What we're doing here is exactly that. So now K is alpha times phi pred transpose here. And then F sample is a sample from a multivariate normal with zero mean and a covariance equal to K. Yeah? So when we sample from that and then we plot X versus those flattened samples, we get the same thing that you've just been doing by sampling W and then sampling phi pred. Furthermore, we can look at what we looked at in the lecture to see what that covariance function looks like. Interesting. So notice this covariance function, actually all the detail in the center here is kind of lost, because as we get to -1 and 1, we start seeing large values, like 40. So sorry, I've sampled beyond that. I've sampled beyond X pred must be going a little bit beyond -1 and 1. So we start seeing large values as we get outside the -1 to 1 region, which is indicative of what actually happens to these covariances as you leave -1 to 1. So you can see the effect that you see in the samples, which is that as you leave this region, or as you start getting close to 1 and -1, you start getting large values in the variance. You can see that marginally in the covariance matrix here. So this is the same visualization of the covariance matrix, but being applied, instead of to that RBF covariance, being applied to the covariance that we've been sampling from for these parametric models. Okay, now because the full model involves taking F and corrupting it with noise, we can see and we're saying that noise is sampled from an independent Gaussian distribution. Now, two multivariate Gaussians added together, the result is the mean is the sum of the means, and the covariance is the sum of the covariances. So we know immediately, without doing any complicated maths, just from properties of Gaussians, that the resulting marginal distribution must be Y is sampled from a Gaussian with zero mean and a covariance which is F's covariance plus epsilon's covariance. So that's now the noisy system. And look what they look like now. Yeah? Samples with a little bit of noise on. Of course, they're not really continuous samples anymore. So really what should happen is that, but we're seeing, just visualizing the noise, that they're jiggling around a little bit around the process. So you can then increase the noise value, and then you get noisier functions. So this is a combination of a larger noise. Here I've set the noise to 1 with those same functions underlying things before. Now, the next bit is, okay, what can we do if we specify the covariance function directly? So this is the covariance function we looked at in the lab, and what I've done is define a covariance, I've called it kern because sometimes people call these kernels because they are Mercer kernels, positive definite functions. I haven't sort of mentioned that bit yet, so I've called it kern because they're kernels in the terms of they fulfill the same definitions people would talk about for kernel functions in machine learning, that they're positive definite. They have to be positive definite to be valid covariance matrices. So I'm defining kern here, and it's got a variance parameter and a length scale parameter, and it's just what we said in the lectures. And then, okay, this is not an efficient way to do it, but it's a clear way to do it. We're going around setting k is equal to be the size of the prediction vector and filling in values of k using the kernel function with particular variance alpha and a particular length scale given by length scale. So if I run that, we can now plot the resulting covariance. So it's quite a large bandwidth here, right? So the bandwidth we saw in the lecture was shorter than that. Here we're seeing larger correlation. But this is the same type of covariance we saw earlier on in the lecture. And now I can do the same thing again. The same thing I did with that. This is exactly the same thing we did the polynomials. So mean 0, covariance is equal to k. Sample from the multivariate normal, with that being the case, and plot the results for 10 different samples. Okay, so the length scale is quite long. So what I get is very flat functions. And I can change that by just changing the length scale to something shorter. So if I make the length scale 1, then I get something shorter here. The reason, so I've got an issue here, and the reason I'm realizing I set that length scale so long is what's going on here? Why is everything too short? What did we do in the last lab session that I haven't undone and I forgot to undo? So this will be true for you as well. That length scale was a reasonable length scale, but not a reasonable length scale given that we've compressed the input scale of the data. So I was confused about why I'd set a stupidly large length scale. It wasn't a stupidly large length scale, but it needs us to re-include the data again in order for it. We basically have scaled the data down to be -1 to 1. The length scale of 10 is reasonable for this data. It's not reasonable for the new data. So that's a bit annoying. I should fix that in the lab. Apologies for that. Where do we compute? So I could take this, couldn't I? Edit, copy, cell, and then so we need to go beyond weight space view, function space view, down here. Okay. Oh no! That failed completely, didn't it? Why is that? So I know what I did wrong. I will have forgotten to copy it correctly. I have got internet connectivity, so the top one should work now. So I didn't use the right Mac key commands to copy it. I used so it was above there, wasn't it? So I just want to make sure that the parameters are a bit more interpretable. That's why I'm bothering to revisit this. And then xpred. Where did I define xpred first of all? Sorry about this. This is a consequence of merging two labs that weren't merged before and then not paying attention to the results of the merge. Xpred. Xpred. Xpred, here we go. So that's, oh, hit the wrong thing. That's the, just setting up the data set to what it was again before we rescaled the input data, yeah? That's the thing I'm trying to fix there. So if I put that down here, hopefully that loads it in. Yeah. And now I'm going to put the length scale back up to 10. So now the length scale has an interpretation in years. Okay, that's a bit better, isn't it? Yeah? So the length scale's got an interpretation in years. So it's saying these functions vary over about 10 years. So humans improve at something related to a 10-year time scale. And so there's the updated covariance function. And now if I do samples from that, I see this, right? Okay, so across 1880 to 2020, this is my prior belief about how human performance varies across those years. So it doesn't have the problems with scaling exhibited by the polynomial basis. So we can reset our data from the Olympics matrix, yeah, that's what I've just done, and show samples computed across the actual years. So in fact, that's what I was trying to do here. Look at that, I'm ahead of myself already. And now we can make predictions directly using this structure of the covariance matrix. So the next bit in the lab is to take our understanding now of how we make predictions across f star and f, or y star and y, and just build that directly. So what this next bit of code does is it sets up some covariance function parameters. It then constructs the three different kernel parts. It constructs k, it constructs k star, and k star star. So k is the training data covariance. K star is the covariance between the training data here and the test prediction data. And k star star is the covariance between the test data and itself. So we're just putting it in these matrices. So running that, now I've got this matrix full K. So full K, oh, it didn't come out that well. Why does that not come out that well? The color's not very good. Something's wrong. So I've got a problem here. What's my problem? Have I reset x? Did I miss? X is data x to 1. Xpred is the lin space. So I'm trying to visualize this matrix here, and it's not looking correct because in the top here there's something wrong. Let me just look at x, k itself. Apologies. Oh no, that looks all right. So this is the covariance for the training data. Let's do print x. Somehow these x is still scaled incorrectly. Bugger. I think if I rerun that, then that'll fix it. I think that's fixed it. Let's have a look. Sorry, I was still using x for one of these nasty assignment errors that I talked about yesterday, I think, was occurring there. What's happened is I tried to reset. Okay, what's the error that occurred there? We scaled x from before, right? And when we scaled x from before, x was set to be equal to data x in this way, which I think was probably giving us a reference. So in effect, we scaled data x in this way. I've now loaded in x again, but I didn't load in data x, I loaded it in this other way. So data x was actually scaled in the old way. This is a nasty sort of bug that you can get with Python sometimes, which is frustrating. And hopefully now that should have fixed that. So now as I come through, x should be back to yes. Okay, so I've now so I had sort of the training data scaled because of these nasty assignment things. So let me just get rid of that, get back to what it should be. A consequence of my fix from the stuff before. Full K, sorry. So the point about this bit is I wanted to show you the full covariance between the training and the test, which is always implicitly there, right? So this is its structure. So given the length scale we have some detailed structure in the training data because the Olympic years are missing in the First and Second World War. So you can see the training data is ordered by the year in which they occurred, but some years are missing. So you'll see a little bit of a clustering structure in the top here. So that's like the years before the First World War, then there's the First World War, the years before the Second World War, Second World War, and then the years of the Olympics into the modern era, where we're seeing just the standard structure. Now we're asking to predict at a much more fine resolution when we're looking at the test data. So this is like every year or something like that. So we see more correlations between the places where we're trying to predict. And then what we also see is the cross correlations between where we're trying to predict and the training data. So those are the 4 blocks we have in our training and test data. So the banded structure we observe is because some of the training points are close to the test points. Yeah? So that's why we get this cross correlation between training and test points. So now we're just going to compute the distribution over f star, which we've sort of shown in the lectures. Well, we didn't derive this, we just gave this as a result, is given by a covariant Gaussian with mean mu f and covariance cf. So let's do that. So I'm just computing, what am I computing here? I'm defining a variable which is the inverse of k plus sigma squared I times k star, because that appears twice. That appears here, k star times k plus sigma squared I inverse, and here. So I might as well pre-compute that. That's often, in support vector literature, that type of thing is called the alphas, so I called it A. And then I'm computing mu f given that. So mu f given that is just A transpose Y, and the covariance, though, is k star star minus A transpose k star. So that's what that's saying there. We've just combined that as convenience. So let's see what the posterior covariance is. So this is the posterior covariance over the training data. So what you're seeing now is larger values. Sorry, it's a bit unclear. On my screen it's clearer. We're seeing larger values of variance where there's no data. So this is Second World War, this is First World War. But in general, what happens at the ends, so the largest variance is at the ends as you leave the data region. And that's just visualizing CF, which is this object here. Okay? So let's plot those predictions. So this is the mean prediction, plotting mu f against xpred. So it's quite wiggly because we've chosen a particular length scale that makes it wiggly, and then we can also compute, as we did before for the polynomial, the variance of the predictions. So there's the variance. We see it's large before the Olympics start, and then this is oscillating around. It doesn't know what happened in the First World War, it doesn't know what happened in the Second World War, and then it's large like that to the end. So that's our prediction from the Gaussian process. So what I want you to do is get through that, and then do what you did for the polynomial before, which is try changing the parameters of the covariance function and the noise to see how these predictions change, and try sampling from the conditional density to see what your predictions look like. So in particular, what happens if you try and sample from the conditional density, the probability of f star given f, in regions a long way in the future or the past? What happens to those samples? And how does it compare with the sort of results you did in the polynomial model? Once you've done that, we'll have a little pause and perhaps go on. The next part of the lab is actually to do similar things, but instead of defining all these covariances yourself, you use gpi to define the covariance, and then you can automate things like the plotting and the model optimization, and you set the parameters of the kernel by changing the parameters of objects. So the first part of this next section of the lab is actually about telling you to how to apply those linear algebra operations that we've just seen in the lecture. And then after we've done that, we're going to move on to this section, which will use different covariance functions. But before we move on to that section, I'll spend a bit more time talking formally at the lecture. So get up to this point here. So stop before the start of where you start using Gaussian process models with GPy. Okay? Any questions?
So how long is going to be this? Half an hour again, or?
I think we'll probably go for 40 minutes.
Okay.
So just to make sure, so you're not feeling rushed, and you may end up with the same problems I had from compressing the lab together, I think, because you're going to find when you first try the GP that we've squeezed, you need to reload the data in, basically, at the beginning of the RBF section. So that people might have a bit of difficulty doing that. So if you, we'll go till 3:30 on this section, and then I'll go back to talking, and then we'll finish off having a look at this section here into the end. Okay? Questions?
So for Gaussian processes, it's not that important to normalize the data?
It might be, depending on, bear in mind the polynomial is a Gaussian process at the end of the day. And for that model, it would be important to normalize the data. But for these stationary covariance functions, what you need to do is set the length scale correctly. So if you initialize the length scale correctly, you can have bad things happen. So for example, if I initialize this length scale here to 1, so it's 8 at the moment. If I change it to 1, okay, so now look at this. It's almost diagonal, the training data, and there's much less correlation with the test data. And then if we look at samples, well, if we look at the predictions, what we'll see is that this is the posterior covariance, which has this funny structure, and that structure emerges when we do predictions like that. There's the mean prediction, because the length scale is too small, so it thinks things can vary in 1 year, but the Olympics only occur every 4 years. So if you combine now the model and the data, it's saying, well, things are varying so quickly between the Olympics that I can't say much about what's going to happen. And bear in mind something here, this covariance is zero mean, which is not sensible because we know this data is not zero mean. So what you're seeing going on now, as I've reduced the length scale, is the mean is fluctuating wildly to interpolate at the data points. If we then look at the variance, the error bars, we see it's basically saying, I don't know what's going on. It's constrained to be zero mean, and so what happens is, away from the data, and the standard deviation looks like it was 8 at the prior. So away from the data, in years like this in the Second World War, it just reverts to the prior, because there's no information moving between the data and the observations. And even at the data, it just flies up, but then it believes that human performance can vary on a 1 year time scale. So the predictions between the data points are large. Now sometimes people say, oh, it's overfitting. I don't think it's overfitting. It's because it's not saying it's sure about what happens. It's saying I have no idea what happens. I think overfitting is a bad word. It's just combining the prior you've given it with the posterior. Now, a bad thing that happens if you even try and optimize this model is this type of model, this type of covariance, becomes unidentifiable with white noise. And actually it will end up deciding that the whole thing is just noise, potentially, just in terms of finding a local minima. But we'll revert back to that in the afternoon lecture. So you don't necessarily have to scale the data, but you have to be careful about how you initialize your parameters in order to get sensible predictions. So if on the other hand we thought that human performance varied over more like 40 years, which I've just set there now, then we see much stronger correlation structure in the full covariance there, and we'd see predictions that tend to smooth the data much more. Yeah? Than our initial attempts. So look at how smoothing that is. Now what the correct answer is perhaps a matter for debate. I quite like that one. That's quite nice, isn't it? So, but you know, I'm not saying that's correct, but we can optimize over these parameters and see what the model thinks. But in this case, it's a much smoother interpolation because the prior says that these functions vary over the scale of 40 years. So we'll come back how to fit those parameters in the next lecture, but for the moment just go through and have a play with those parameters and perhaps also a play with alpha, the overall variance, and a think about what that's meaning. Yeah, sorry, the standard deviation is 4. I said 8 earlier, it's 4 because it's 16, square root of 16, which is alpha set to. Okay, other questions? Good. You all had big lunches. You're all very quiet now. You were all much more attentive before lunch. Okay. Right.